In the previous module, we have learned about the Frobenius method of solving the second order differential equation near the singular point. In this module 6, we will take up few examples about this method. We will go through step by step for better understanding of this Frobenius method. In this module, we will take few examples so that Frobenius method can be learned step by step. The problem says that you have to find two solutions of the Bessel equation of order half given by t square d2x dt square plus t dx dt plus t square minus 1 by 4 into x equal to 0, where t lies between 0 and infinity. The given equation has a regular singular point at t equal to 0 as t into pt is equal to 1 and t square into qt equal to t square minus 1 by 4, where here pt is 1 by t and qt is t square minus 1 by 4 divided by t square, and they are both analytic at the point t equal to 0. We assume the solution of the form x t equal to summation n equal to 0 to infinity a n t to the power n plus r, where a 0 not equal to 0, given by equation number 3. Differentiating 3 twice, we will get x dash t equal to summation n equal to 0 to infinity n plus r a n t to the power n plus r minus 1 and x double dash t equal to summation n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r minus 2, given by equation number 4 and 5 respectively. Substituting x, x double dash and x dash in the given differential equation, we will get summation n equal to 0 to infinity n plus r minus 1 a n t to the power n plus r plus summation n equal to 0 to infinity n plus r a n t to the power n plus r plus summation n equal to 0 to infinity a n t to the power n plus r plus 2 minus 1 by 4 plus summation n equal to 0 to infinity a n t to the power n plus r, which after simplification gives summation n equal to 0 to infinity n plus r minus 1 plus n plus r minus 1 by 4 a n t to the power n plus r plus summation n equal to 2 to infinity a n minus 2 t to the power n plus r, given by equation number 6. We now equate the sum of coefficients of like powers of t to 0, and this gives f r a 0, which is equal to r into r minus 1 plus r minus 1 by 4 into a 0, which is equal to r square minus 1 by 4 into a 0 equal to 0. F r plus 1 into a 1 equal to 1 plus r into r plus 1 plus r minus 1 by 4 into a 1, which simplifies to 1 plus r whole square minus 1 by 4 into a 1 equal to 0. And lastly, f n plus r into a n is equal to n plus r whole square minus 1 by 4 a n is equal to minus a n minus 2, where n greater or equal to 2. Now, equation 7 is the indicial equation, and the roots of the indicial equation are half and minus half, which we denote by r1 and r2. For r1 equal to half, we set a 0 equal to 1, and by equation number 8 we will get a 1 is equal to 0. The recurrence relation 9 will imply a n is equal to minus a n minus 2, divided by f of n plus half, which is equal to minus a n minus 2 divided by n into n plus 1, where n greater or equal to 2. This recurrence relation and equation 8 will imply that all odd coefficients a3, a5, a7 all are zeros, and the even coefficients will be given by a2 is equal to minus a0 by 2 dot 3, which is equal to minus 1 by 3 factorial. Similarly, a4 equal to minus a2 by 4 dot 5, where we substitute the value of a2 from here to get equal to 1 by 5 factorial. In the similar way, we can calculate a6 equal to minus 1 by 7 factorial and so on. Now, by induction, it can be easily shown that a2n is equal to minus 1 whole to the power n divided by 2n factorial into 2n plus 1, and hence we conclude x1 t is equal to t to the power half multiplied by 1 minus t square by 3 factorial plus t to the power 4 by 5 factorial minus t to the power 6 by 7 factorial plus dot 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 is the solution of the given differential equation 1. This solution can be rewritten in the form x1 t is equal to t to the power half divided by t multiplied by t minus t cube by 3 factorial plus t to the power 5 by 5 factorial minus t to the power 7 by 7 factorial plus dot dot dot, which is equal to 1 by root t into sin t. For R2 equal to minus half, let A0 be equal to 1, and since R1 minus R2 equal to 1, we may have a problem here while calculating the coefficient A1. But however, equation 8 is automatically satisfied regardless of the value of A1. We will set A1 equal to 0, and then the recurrence relation becomes a n equal to minus a n minus 2 divided by n minus half whole square minus 1 by 4 equal to minus a n minus 2 divided by n square minus n, which is equal to minus a n minus 2 divided by n into n minus 1, where n greater or equal to 2. We again calculate the odd coefficients and which will be equal to 0, and the even coefficients will be given by a2 is equal to minus a0 divided by 2 dot 1, which is equal to minus 1 by 2 factorial, a4 equal to minus a2 by 4 dot 3, and we substitute the value of a2 from here in this place to obtain 1 by 4 factorial. In the similar way, we can calculate a6 equal to minus 1 by 6 factorial and so on. Using the method of induction, we again see that a2n is equal to minus 1 whole to the power n divided by 2n factorial. Hence, x2t is equal to t to the power minus half multiplied by 1 minus t square by 2 factorial plus t to the power 4 by 4 factorial minus t to the power 6 by 6 factorial plus dot dot dot, which is equal to 1 by root t cos t, and this is the second solution of the given differential equation 1. The following calculations enable us to write the general form of the second solution when r1 minus r2 is 0 or a positive integer. Let r1 minus r2 equal to n0. The indicial equation can be written as r into r minus 1 plus r p0 plus q0, which is equal to r minus r1 into r minus r2, or r square minus r plus r p0 plus q0, which is equal to r2 minus r into r1 plus r2 plus r1 r2, and this implies the sum of the roots r1 plus r2 is equal to minus p0 plus 1, which implies r2 is equal to minus p0 minus r1, and hence n0 is equal to r1 minus 1 plus p0 plus r1, implies n0 plus 1 is equal to 2 r1 plus p0, and let that be equal to k. Now, since we have one non-zero solution of the given differential equation 1, we can utilize the reduction of order method to find the second linearly independent solution. Let x1 equal to t to the power r1 summation n equal to 0 to infinity a n t to the power n. Then x2 is v times x1, where v dash is equal to 1 by x1 square e to the power minus integration pt dt. Please note here t into pt is equal to p0 plus p1t plus p2t square plus p3t cube plus dot dot dot, and hence we can get pt by dividing the whole expression by t, which is equal to p0 by t plus p1 plus p2t plus p3t square plus dot dot dot. Therefore, v dash is equal to 1 by t to the power 2 r1 into summation a n t to the power n square e to the power minus integration p0 by t plus p1 plus p2t plus p3t square plus dot 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 dt, which is equal to 1 by e to the t to the power 2 r1 summation a n t to the power n whole square 1 by t to the power p0 e to the power minus integration p1 plus p2t plus p3t square plus dot dot dot, which we can write as 1 by t to the power k gt, where gt is equal to e to the power minus p1t plus p2t square by 2 plus dot 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 plus pn t to the power n by n plus dot 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 divided by summation a n t to the power n whole square. And g0 is equal to 1 by a0 square. gt is equal to b0 plus b1t plus b2t square plus dot 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 bk t to the power k plus dot dot dot, or v dash is equal to b0 t to the power minus k plus dot 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 plus bk minus 1 t to the power minus 1 plus bk plus bk plus 1 t plus dot dot dot. Integrating, we will get Vt is equal to b0 multiplied by t to the power minus k plus 1 divided by minus k plus 1 plus bk minus 1 log t plus bk t plus bk plus 1 t square plus dot dot dot. Therefore, x2t is equal to x1t into Vt, which is equal to summation n equal to 0 to infinity a n t to the power n plus r1 into b k minus 1 log mod t to the base e plus b0 t to the power minus k plus 1 divided by minus k plus 1 plus dot dot dot, which is equal to b k minus 1 log of mod t into x1t plus summation n equal to 0 to infinity a n t to the power n into t to the power r1 into t to the power minus k plus 1 multiplied by b0 plus b1t plus dot dot dot. This can be written in the simplified form as x1t bk minus 1 log of mod t plus t to the power r1 minus k plus 1 multiplied by summation n equal to 0 to infinity a n t to the power n multiplied by summation n equal to 0 to infinity b n t to the power n, which is equal to x1 t bk minus 1 log of mod t plus t to the power r2 summation c n t to the power n. Therefore, x2 t is equal to x1 t bk minus 1 log of mod t plus t to the power r2 summation c n t to the power n. Now, if r1 is equal to r2 implies k is equal to 1 implies bk minus 1 is equal to b0 is equal to 1 by a0 square, which is not equal to 0. So, in this case the term containing log of mod t is surely present in the solution. However, if r1 is equal to r2 is equal to k minus 1 is a positive integer, then sometimes bk minus 1 is not equal to 0 and logarithmic term is present, and sometimes bk minus 1 is equal to 0, and hence we have a solution of the Frobenius type. The practical difficulty here is that we cannot readily find bk minus 1 because we have no direct means of evaluating the coefficient of gt. In any event, we at least know that in case 1 and case 2, when bk minus 1 is not equal to 0 and the method gives only one solution, the general form of the second solution is x2t is equal to x1t bk minus 1 log of mod t plus t to the power r2 multiplied by summation n equal to 0 to infinity c n t to the power n, where c n are certain unknown constants to be determined by substituting it directly into the differential equation. We have just solved Bessel's equation or order half about the point t equal to 0, which is a regular singular point. We will now take an example where t equal to t0 is not a regular singular point, that is, it is an irregular singular point. We will see how to tackle this kind of problems now using the Frobenius method. Method of Frobenius may not work to find a Frobenius series solution around a singular point t equal to t0, which is not a regular singular point, that is, t equal to t0 a singular point and it is an irregular singular point. We consider the differential equation x double dash plus 1 by t square x dash minus 1 by t cube x is equal to 0. Since t equal to t0 is a singular point of the equation 10, we will now check if t pt and t square qt, where pt is equal to 1 by t square and qt is equal to minus 1 by t cube, are analytic at the point t equal to 0 or not. Therefore, we have t minus 0 pt, which is equal to 1 by t, and t minus 0 whole square qt, which is equal to minus 1 by t square, and we can see both these expressions are not analytic at t equal to 0 because they are both undefined at the point t equal to 0, and therefore t equal to 0 is an irregular singular point. We may observe that x1 is equal to t is a solution of the given differential equation 10, and this can be easily obtained if you substitute x1 equal to t in the given differential equation 10, and you will see that it satisfies both the left hand side and the right hand side. So, once you prove that x1 equal to t is a solution of the given differential equation 10, then you can take another solution x2 of the form x2 equal to v x1, where x1 is equal to t and v is a function of t which needs to be determined. By the method of reduction, we have x2 is equal to integration 1 by x1 square e to the power minus integration pt dt is equal to integration 1 by t square e to the power integration minus 1 by t square dt. And if you integrate this, you will get this is equal to minus t e to the power 1 by t, given by equation number 11. Please recall a Frobenius series solution given by x t equal to t to the power r summation n equal to 0 to infinity a n t to the power n, where r may be a negative integer, a fraction, or even an irrational number. The solution 11 obtained can be rewritten as x t is equal to minus t multiplied by 1 plus 1 by t plus 1 by 2 factorial t square plus 1 by 3 factorial t cube plus dot dot dot, given by equation 13. We now compare equation 12 and equation 13, and we will get t r equal to 1 and n equal to minus 1, minus 2, minus 3, and so on. Thus, in 13 n has negative values, and therefore 13 is not in the form of Frobenius series. In our next example, we consider the differential equation x double dash plus p by t to the power b x dash plus q by t to the power c x equal to 0, given by equation number 14, where p and q are non-zero real numbers and b and c are positive integers. From equation 14, it is clear that t equal to 0 is an irregular singular point if b is greater than 1 or c is greater than 2. To calculate this, please denote capital Pt is equal to 1 by t to the power b and capital Qt is equal to 1 by t to the power c, and then you calculate t into Pt and t square into Qt. The expression which you will get should not be undefined at the point t equal to 0. So, we find a condition for which the expression is undefined at the point t equal to 0, and that condition is given by b is greater than 1 or c is greater than 2, and only then you can conclude that t equal to 0 is an irregular singular point. If b equal to 2 and c equal to 3, then we have to show that there is only one possible value of r for which there might exist a Frobenius series solution. Similarly, you have to show that r satisfies a quadratic equation, and hence we can hope for two Frobenius series solution corresponding to the roots of this equation if and only if b is equal to 1 and c is less or equal to 2. We take b equal to 2 and c equal to 3, then our equation 14 reduces to t cube x double dash plus p t x dash plus q x is equal to 0. We put x t is equal to summation n equal to 0 to infinity a n t to the power n plus r, and we get t to the power r multiplied by summation n equal to 0 to infinity a n plus r minus 1 t to the power n plus 1 plus summation n equal to 0 to infinity a n p n plus r t to the power n plus summation n equal to 0 to infinity a n q t to the power n is equal to 0. Equating the sum of coefficients of t to the power 0 from both sides, we will get a0 pr plus q a0 equal to 0, which implies a0 multiplied by pr plus q equal to 0. Since the indicial equation is linear, there is at most one possible value of r, which is r equal to minus q by p. If b is equal to 1 and c is less or equal to 2, say for example we take c equal to 2, then the given equation 14 reduces to t square x double dash plus pt x dash plus qx equal to 0. We again set xt is equal to summation n equal to 0 to infinity a n t to the power n plus r. We substitute it in the given differential equation to get t to the power r multiplied by summation n equal to 0 to infinity a n plus r minus 1 into t to the power n plus summation n equal to 0 to infinity a n p n plus r t to the power n plus summation n equal to 0 to infinity a n q t to the power n is equal to 0. Equating the sum of coefficients of t to the power 0 from both sides, we will get a0 into r minus 1 plus a0 into pr plus a0 into q equal to 0, which will imply r into r minus 1 plus pr plus q equal to 0. Since p and q are non-zero real numbers, r satisfies the quadratic equation. Hence, there are two Frobenius series solutions, namely x1 equal to t to the power r1 summation n equal to 0 to infinity a n t to the power n and x2 is equal to t to the power r2 summation n equal to 0 to infinity a n t to the power n, where r1 and r2 are the roots of equation number 15. In this module, we have learned few examples which better explains the Frobenius series method step by step. In our next module, we will continue with the examples of Frobenius series solution for better understanding of this method. Thank you.